Very good morning to you all. So in today's lecture, I will be discussing about the Bremsstrahlung radiation and then the angular distribution of radiation. We have already derived the formula, Larmor's formula for power radiated by a charge which is accelerated, and if it is a relativistic, then gamma to the power 6 terms appears extra in the Larmor's formula. Otherwise, so let us now understand what are Bremsstrahlung radiation. Bremsstrahlung is a German word. If you look at the dictionary, Bremsstrahlung meaning is a breaking radiation. Breaking radiation is called Bremsstrahlung. Let us understand what exactly it is. The power radiated by a point charge is given by the formula 1 upon 4 pi epsilon 0, 2 upon 3 q square a square upon c cube, and gamma to the power 6 appears if the particle is moving with the relativistic speed. As told you earlier, the power is proportional to the acceleration square. So it is proportional to plus and minus a square. That means either the charge is accelerated or decelerated. The distribution of power is given by this formula. So distribution of radiation is same for accelerating and decelerating particle with the same acceleration or deceleration. When a high-speed electron hits a metal target, it rapidly decelerates, giving off a radiation, and we call this radiation as Bremsstrahlung radiation. At your intermediate classes and the BSc classes, you must have read about the X-ray radiations. There are two types of X-ray radiations we normally talk about. One is continuous X-rays and other is called characteristic X-rays. You must have gone through the explanation of characteristic X-rays that whenever a high energy electron penetrates an atom and knocks out the electron from the innermost cells like K cells or L cells or M cells, then the vacancy of that electron is filled by the transition of electron from the upper state to the state from where the electron is knocked out. And the corresponding radiations are K alpha, K beta, K gamma radiations. These are called characteristic radiations. But when we talk about the continuous radiations, what you must have studied that the background consists of radiations from a minimum frequency. Minimum frequency is defined by the Duan-Hunt limit, and then there is no limit. It gives basically radiation of almost all the frequencies. Now the answer to this question is that it is because these radiations are Bremsstrahlung radiation, because when the electrons goes inside the material or inside, when the electrons bombard the high Z target, they are decelerated by different amounts, and when they are decelerated, they basically gives us radiations, and we call them as Bremsstrahlung radiations. So continuous radiations are nothing but the Bremsstrahlung radiation. You will also come across what is called inverse Bremsstrahlung. So Bremsstrahlung here is the process of breaking radiation by or from a decelerating electron. If a charged particle basically absorbs radiation, if an electron absorbs radiation, then the process is called inverse Bremsstrahlung. In a chapter in your course on laser physics, you will come across inverse Bremsstrahlung because that is a most common process there. Now I will have some discussion on linear acceleration once again. We will assume as if an electron is moving with a velocity b and the acceleration a, and the velocity and acceleration are in the same direction. We derived the formula for the power radiated in the last lecture. It is 1 upon 4 pi epsilon 0 2 q square a square upon 3 c cube into gamma to the power of 6. In some textbooks, you will find that they write this a square upon c cube term as beta dot square upon c. What is beta? Beta is b upon c. So beta dot becomes a b dot upon c, and therefore a square becomes beta dot square upon b dot square upon c square, and we have a c in the denominator, so it becomes beta dot square upon c. So this is another way of writing down the formula. If you recall the relativistic formula of the momentum m is p is equal to m0b. In fact, in place of m, it should be m. The formula is normally written as gamma into m into b, and m here should be it by rest mass. Either you define this m as a rest mass, or you write this to be equal to m0, because p is equal to m into b, or gamma into m into b. If you differentiate this expression for the momentum, find out the value of a p dot, you can easily verify that dp over dt comes out to be m gamma cube into b dot. You can work it out. So by making use of this formula for the momentum, it is the formula for a relativistic particle. It comes in a special theory of relativity. So b dot is now equal to dB upon dt, and this is 1 upon m gamma cube into dP upon dt. So we replace this b dot. What is b dot? B dot comes here. B dot is nothing but the acceleration. So we replace this by here, and the formula becomes dP upon dt. P is equal to 1 upon 4 pi epsilon 0 2e square upon 3 m square c cube into dP upon dt whole square. So rate of change of momentum of a particle is also given by the rate of change of the energy of the particle. So you already know the Newton's second law of motion. Newton's second law of motion says that F is equal to dP upon dt. So dP upon dt is the rate of change of momentum, that is equal to force. This comes from Newton's second law of motion. Similarly, if you recall work energy theorem, so work done is nothing but the change in the energy of a particle. So rate of change of energy of a particle with distance is also F. So the first term and the second term together is the Newton's second law of motion, and the second term and the third term together is work energy theorem. So we can replace dP over dt as a dE over dx. So formula for the power radiated now becomes equal to P is equal to 1 upon 4 pi epsilon 0 to E square upon 3 m square c cube, and then dE upon dx square. So this formula tells us that the radiated power depends upon the rate of change in particles energy with distance. This is the formula. It's not a general formula. This formula is applicable for a particle which is moving in a straight line, which with velocity and the acceleration are in the same direction. Now, so it depends upon dE over dx. It's a very important formula. Now to move further, we take now the ratio of P to dE over dt. dE over dt is basically the rate at which the power is supplied to the particle. So power radiated, P is the formula for the power radiated, that comes from the Larmor's formula, divided by power supplied, that is dE over dt. So it's a dE over dx divided by dE over dt. So this becomes a dE upon dx. So this dE upon dx, if you look this formula, so it becomes now E square upon, we can rearrange these terms here as E square upon MC square divided by MC. I will explain you why have I done it like this in this formula. So R0 here is the classical electron radius. Don't confuse with the classical electron radius. It is 1 upon 4 pi epsilon 0 E square upon MC square, because we have 1 upon 4 pi epsilon 0 and then E square upon mc square. You club these terms together, it becomes the classical electron radius. Divided by mc square. As I told you that mc square, m here is the free, in fact, the rest mass. So mc square is nothing but the rest mass energy of a particle. So if you look at this formula, it is Pt upon dE over dt. That means a rate of energy radiated to the energy supplied is 2 upon 3 into R naught upon mc square into dE upon dx. And you will see, if you make a calculation, this term is much smaller than 1. I will explain you why. It is because the power, if you first of all R0, you take the rest mass of an electron, 9.1 into 10 to the power minus 31, make a calculation of this classical electron radius, it comes out to be 3 into 10 to the power of minus 15 meter. The rest mass energy of the electron is 510 kilo electron volt, or if you write in million electron volt, it is 0.51 million electron volt. If you calculate this ratio, it is energy upon distance, and here it is a dE upon dx. So mc square upon r0, the ratio of rest mass energy to the classical electron radius is 2 into 10 to the power of 14 million electron volt per meter. So power radiated, I have written here this to be much less than 1. You have to understand this. The power radiated away is negligible in comparison to the rate at which the energy is being pumped into the particle, unless one pumps the energy at a rate dE upon dx comparable to the rest energy of the particle mc square in a distance r0. Because this formula here, dE upon dx is energy upon distance, r0 upon mc square distance upon energy. So it is basically a competition between these two terms that takes place, and the value of this term here is 2 into 10 to the power of 14 million electron volt per meter, unless and until we have the value of a dE over dx to be larger than this value. If it is equal to this value, then we can say, okay, our Pt upon dE over dt will be equal to just 2 upon 3. 2 upon 3 is close to 1, we can say. But otherwise, you see, what are the practical problems of having dE over dx to be of this order? So we make another small calculation, because R0 is very small and it is difficult to put so much energy into the particle over such a short distance, because R0 is 10 to the power minus 15. So I give you an example. Suppose theoretically, if you put 200,000 volts in a distance of 10 to the power minus 15 meter, then this voltage corresponds to the energy to be equal to EB in joule. You further convert it into the electron volt, it becomes 2 into 10 to the power 5 electron volt divided by 10 to the power of minus 15 gives us 2 into 10 to the power of 14 million electron volt per meter. Don't get confused. 10 to the power 5 upon 10 to the power 15 minus 15 gives us 10 to the power of 20. So 10 to the power of 20 electron volt. If you convert it in million electron volt, so it's a 2 into 10 to the power 14. So you can see, putting this much of voltage in such a short distance is always impossible. So that is the reason why the particles in linear accelerators lose an insignificant amount of energy to the radiation, because this term is much smaller. So please make these calculations to understand these things in a better way. Now, a very common question that is asked, that how the electron orbit are not stable. So I'm going to consider basically the hydrogen atom case again, that we have a nucleus and the surrounding electrons, the electrons are moving in an orbit of radius to be equal to r with a velocity b. You already know that if a particle having a charge q moves with a velocity b in a circular path of radius to be equal to r, its centripetal acceleration is given by a to be equal to b square by r. So total power radiated by the electron is given by the Larmor's formula. So Larmor's formula is 1 upon P is equal to 1 upon 4 pi epsilon 0 2e square upon 3c cube into a square. So this now becomes equal to, replace a by b square by r. So it becomes b by v square by r whole square. Now let us quickly see the equations for basically calculating the relation between the velocity and the radius and the energy. The necessary centripetal force required by the electron to move surrounding the nucleus is given by the electrostatic force of attraction between the nucleus and the electron. So mb square by r becomes 1 upon 4 pi epsilon 0 e square upon r square. I am considering the hydrogen atom case. And in case of hydrogen, we have one proton in the nucleus and which had a similar charge to the electron. That is why we have E square here. So we now cut one R from both sides, and then B square becomes equal to 1 upon 4 pi epsilon 0 E square upon R. We substitute it here and put back into our formula. Again, there are several ways of doing this. And once you do this, then the value of P comes out to be 3 into 10 to the power 11 electron volt per second. That means the electron in an orbit, in its orbit, will radiate energy at 3 into 10 to the power of 11 electron volt per second, because it is accelerated, and you all know that accelerated charge emits energy, so therefore it will emit at this rate. Let us now calculate the total energy of the electron in its orbit. So the total energy is given by the sum of the kinetic energy and the potential energy. So it is half mv square. If b is the velocity, so kinetic energy becomes half mv square. And the potential energy is 1 upon 4 pi epsilon 0 q1 q2 upon r. Q1 is electron, q2 is proton. One is positively charged, other is negatively charged. So that is why you have a minus sign here. If you make use of this formula again, mb square is 1 upon 4 pi epsilon 0 e square upon r. Divide both sides by 2. So half mb square can be written as 1 upon 8 pi epsilon 0 e square upon r. Put it here. So if you put it here, so 1 upon 8 pi epsilon 0 e square upon r minus 1 upon 4 pi epsilon 0 e square upon r will give you minus e square upon 8 pi epsilon 0 r. And if you substitute all these values, you must have read it comes out to be minus RHC upon n square. R is called Rydberg constant, H is called Planck's constant, and C is the velocity of light. So either way you do it, the energy of the electron in its orbit comes out to be minus 13.6 electron volt. So this is the energy, and this is the rate at which the energy will be radiated out according to the basic principle of classical electrodynamics. So therefore, the time required to radiate this energy exhibited by the electron in its orbit will be given by the energy divided by the rate of decay of energy with time. So if you substitute it, it comes out to be 4.3 into 10 to the power minus 11, because the moment you put the electron in its orbit, in a very short time, after radiating the energy, it will collapse into the nucleus, and an stable atom is not possible. So we can't have a stable atom based on this. It's a very common question that is asked in your examination. So that is why I decided to include it in today's lecture. Now, as I told you in the last lecture, that we will now discuss the angular distribution of radiation. For the case in which the velocity of the particle is parallel to the acceleration, we derive this formula dp upon d sigma is 1 upon 4 pi epsilon 0 q square a square sine square theta upon 1 minus beta cos theta to the power of 5. Beta is b upon c. Then we integrated this and we ended up with a term like gamma to the power of 6 that we got after integration. This is the formula for the power radiated per unit solid angle. For getting maximum radiation, for getting the value of the angle at which this is maximum, we will make use of the maxima and the minima concept of integral calculus. So d over d theta of theta dependent terms, which are sine square theta upon 1 minus beta cos theta to the power 5, this must be equal to 0. So let us now differentiate the terms inside the bracket as the first function into the second function. So first function into differentiation of second plus second function into differentiation of first. So I have considered 1 upon 1 minus b over c cos theta to the power 5 as my first term. So I differentiate the second term sine square theta. It gives us 2 sine theta into cos theta. Secondly, I retain sine square theta as it is. Now I differentiate 1 upon 1 minus b upon c cos theta to the power of 5. So minus 5 comes to the numerator, and then this to the power of minus 5 minus 1, it becomes 1 minus b upon c cos theta to the power of 6. Now you differentiate 1 minus v over c cos theta or 1 minus beta cos theta. So cos theta after differentiation will give us minus sine theta. So minus sine theta will make it plus. So this minus will remain as it is. Now you make some changes into this equation, throw away the common terms, and then we are left with 2 cos theta minus 5 beta sine square theta upon 1 minus beta cos theta. Multiply both sides by this term 1 minus beta cos theta and replace sine square theta by 1 minus cos square theta. We get the equation 3 beta cos square theta plus 2 cos theta minus 5 beta to be equal to 0. It is a quadratic equation in cos square theta. So since it is a quadratic equation in cos square theta, we can apply the formula to find out the roots of this equation for cos theta or theta maximum, means that will give us the maximum value of theta. So this is now minus 2 plus minus under root of 4 plus 60 beta square upon 6 beta. Take out 2 common and it becomes minus 1 plus minus under root of 1 plus 15 beta square upon 3 beta. Now I take the positive value of cos of theta. So that is why I ignore the minus sign, because the quantity inside the bracket is a quantity more than 1. So I consider a positive sign. So in that case, I will end up with the value of cos theta to be less than 1. So let us make a substitution. Let us assume that beta is equal to 1 minus x. When v tends to c, or as velocity will approach to the velocity of light, the value of x will tend to 0, because x tends to 0, beta will tend to 1, and beta is b upon c, so the velocity will tend to the velocity of light. So what you have to visualize that the value of x here is very small. So in order to find out the value of beta square, we can make use of the binomial theorem. So beta square is 1 minus x square. So it is 1 minus 2x. There will be terms corresponding to x square also, but we ignore them. We throw them away. So we have substituted this beta square here by 15 into 1 minus 2x. So this 1 plus 15 becomes 16, and then 15 multiplied by minus 2x will give us minus 30x. So let us now pull out 16 from this square root. So if you pull out 16 from here, so since it is the square root, so we will take out 4 from here, and we are left with 1 minus 15 upon 8x to the power of half. We again make use of the binomial theorem. So this half goes inside, and we have 1 minus 15 upon 16x. And in the denominator, we have 3 into 1 minus x. So the denominator now have -1 plus 4. It's basically 3 minus 15 upon 4 into x divided by 3 into 1 minus x. So I have divided by 3. So 3 minus 15 upon 4x divided by 3 becomes 1 minus 5 upon 4 into x, and 1 minus x to the power minus 1 becomes now 1 plus x. So if you multiply these terms, retaining the terms up to x only, and ignoring all other terms of higher power because x is much smaller than 1, so then we are left with 1 minus x upon 4. We all know that expansion of cos theta for a small value of theta is 1 minus theta square by 2. So 1 minus theta square by 2 is 1 minus x upon 4. So 1 cancels out, minus sign also cancels out. And the value of theta maximum comes out to be under root of x by 2 or under root of 1 minus beta upon 2. Now you can see that as beta approaches to 1, as the velocity of the particle approaches the velocity of light, the value of theta maximum becomes 0. So the donut of in the last lecture I made a statement that donut of maximum radiation is basically towards the direction, it is pushed towards the direction of the velocity or acceleration of the particle. So theta maximum very small. So angular distribution is confined to a narrow cone in the direction of the motion of a particle, because theta is very small, because it is 1 minus beta upon 2. If b is exactly equal to c, theta maximum will be equal to 0. After this, now let us talk about synchrotron radiation. You remember the formula dp upon d sigma is 1 upon 4 pi epsilon 0 r cross u cross a whole square upon r cap dot u whole to the power of 5. Now we consider a case where the velocity is perpendicular to the acceleration. B is perpendicular to the acceleration. So if a B is perpendicular to the acceleration, now the things are not simpler as compared to B parallel A, because when we took B parallel A, then U cross A reduced to a small term. But here it is R cap cross C into R cap minus a V cross A. So we are left with now, we have basically R cross R cap minus B upon C cross A, and we have to take the square of this. So there are ways, because what you can do is you can apply the formula, first of all, BAC minus CAB formula. So although I have taken this square, but that square is here also. The A cross B cross C is B. B is R cap minus B over C, and BAC, it is R dot A minus C comes here. So C into and then R cap dot inside the bracket, we have R cap minus B over C. And then now after simplifying this, we will take the square. So if you leave this as it is, so this is a vector term. This is a scalar term. So here R dot A is square is here. Similarly, R cap minus B upon C square will come here. Now we move on to the second term. The quantity inside the bracket is a scalar quantity, and the vector is A. So A is square, and then R cap dot R cap minus B over C is square, minus twice of basically the term containing both these terms. So 2 times R dot A will come, and then we have basically R cap dot R dot minus B over C, that means this term, and then A dot R, this A vector is dotted with R cap, and then this A vector is dotted with minus B upon C. So you can see 2 times of A into R cap plus A into B upon C. So this is basically the expression for the square of the numerator. Let us now take the value of r. We make use of the spherical polar coordinates. In spherical polar coordinates, what we have chosen the velocity along the z-axis and the acceleration along the x-axis. Suppose r cap is somewhere here. It is making theta angle with the z direction. So this is theta coordinate in the spherical polar coordinate system. Now from the tip of this r cap, you drop a perpendicular in the xy plane, and suppose the foot of perpendicular meets at this point. You join this to the origin of the coordinate system. This angle is phi. Phi is basically the angle again in spherical polar coordinates. And you know that the value of r cap unit vector can be written as sine theta cos phi into r cap plus sine theta into sine phi into j cap plus cos theta into k cap. Because if you write the vector r, then r and r will appear with all the three terms. But to find out the value of r cap, we have to divide it by the magnitude of the vector, and magnitude of a vector is r. So that is why you don't see r here. As I told you just now, the velocity is along the z-axis and the acceleration is along the x-axis. So r cap dot v will be equal to v cos theta, but r cap dot a will be a sin theta into cos phi. You can make use of these expressions to find out this. So you make the substitution here. So these terms has been substituted. They are substituted here. So c square. So be careful while doing all these things. So the value of a dp upon d sigma here will now become 1 upon 4 pi epsilon 0 q square a square upon 4 pi c cube 1 minus beta cos theta cube, and then inside the bracket you will get 1 minus sine square theta cos square phi into 1 minus b square upon c square divided by 1 minus beta cos theta square. Remember, in the case of linear acceleration, we got a term 1 minus beta cos theta to the power of 5 because we have one terms less than the terms here. So this is the value of a dp upon d sigma. If we want to find out the total power radiated, the life is not simpler here because we have theta and phi both. So we have to multiply it by, again, d sigma is 2 r square sine theta d theta into d phi. And if you make the integration, I have not made the integration because it's a long mathematical exercise. If you calculate it, the power in a cyclotron radiations will come out to be 1 upon 4 pi epsilon 0, 2 upon 3 q square a square upon c cube into gamma to the power of 4. Gamma to the power 4 will appear. We will derive as in case of linear, this is for circular. In case of linear, we derived in the last lecture 1 upon 4 pi epsilon 0, 2 upon 3 q square a square upon c cube into gamma to the power of 6. So if we want to write down the relation between the two, then the power radiated in circular case is gamma square times the power in a linear case. When we will talk about the 4 vectors, we will derive another formula, another very generalized formula, where we will take 2 different cases. The first one, when the velocity and the acceleration, they are parallel to each other, and other case will be when the velocity and the acceleration are perpendicular to each other. There also we will derive the formula consisting of gamma square and gamma to the power of 6, and it will be easier for all of you to visualize it in a much better way. So here, except this, it just you have to realize that calculation of this integral is difficult, because it involves sine theta and cos theta both, but it's not impossible. If you want, you can work it out, and it will come out to be the normal formula times gamma to the power of 4. Now I again take a case of the electron, which is moving with a velocity v in an orbit of radius to be equal to r. So here the formula is 1 upon 4 pi epsilon 0 2 e square upon 3c cube gamma to the power of 4, and then B square by R becomes B to the power 4 over R square. The energy expression in relativistic dynamics or in special theory of relativity is given by gamma. It is mc square, and m is equal to m0 upon under root of 1 minus b square upon c square. So we can write this as gamma times m0 into c square. So E divided by the energy of the electron divided by m0 c square. M0 c square is the free energy that I have replaced here. Gamma is replaced by this. So in place of gamma, I have written this to be equal to E upon m0 c square. M0 is the rest mass. In the previous lecture, in fact, there was some problem with the m0. The m0 that I wrote was basically the mass of the rest mass of the electron. So here it becomes now equal to 2 upon 3 E square C upon R square into E upon m0 C square to the power of 4, and B to the power 4 appears here. The energy emitted per cycle of a motion. The energy emitted every cycle. What is cycle? Cycle is nothing but the period of the motion. Period is nothing but the time taken by the particle to complete one rotation. So that is the circumference divided by the velocity is the period of the cyclotron motion, or cyclotron time period also we can call this time. So delta E is P into T. This is the energy emitted every cycle, and the tau is 2 pi R by B. So we multiply this by 2 pi R by B. Since we have R here, so and R is still in the denominator, so one R will cancel, and for energy we will be left with just R in the denominator. Similarly, B to the power 4 divided by B will give us V cube. Cube of the velocity will appear. So if you look at the formula, delta E here, the energy emitted per cycle of the motion, is given by the formula delta E to be equal to 1 upon 4 pi epsilon 0, 4 pi E square B cube upon 3R into E upon m0 C square to the power of 4. So the important result from here, the change in the energy emitted per cycle of the motion depends upon the energy of the particle, depends upon the energy of the particle. Let us make a calculation here. Suppose I have an electron of 500 million electron volt energy. Don't consider this dot. I put some whitener here, but it is still visible. So I have an electron of 500 million electron volt energy. We all know that rest mass energy of the electron is 510 kilo electron volt, or 0.5 million electron volt. If you consider a value of R to be equal to 1 m, you can verify this calculation at your end. The value of delta E, the value of energy emitted per cycle of the motion by the electron, will come out to be delta E to be 10 to the power 4 electron volt. So depending upon the energy of the electron, depending upon the radius of the movement of the electron, you can find out the energy emitted per cycle of a motion. So it is the energy and the radius that puts basically a restriction to find out the value of delta E. So by making these calculations for linear acceleration case and the circular acceleration case, we can calculate which is more appropriate way to exploit for a particular application. So you have basically linear acceleration case or linear radiation case and synchrotron radiation case. Synchrotron radiations are the one which are emitted by a charged particle moving in a circular path, or in general in a curved path. And linear radiations are the radiations which are emitted by a particle in the linear path, in a straight line motion. So that is the difference between the synchrotron radiation and the linear radiation. So that is all about today. So I will stop here, and in the last lecture of this unit, I will talk about the radiation reaction and then Cherenkov radiation, which are also a very important type of radiations.